Physicists use models to explain observations and phenomena. J. Thomson's plum pudding model of an atom consists of a sea of uniform positive charge, which accounts for most of the mass of the atom. Small negatively charged electrons are scattered throughout the atom like plums in a pudding. However, this model was unable to explain results obtained in Rutherford's alpha scattering experiment. Niels Bohr, a Danish physicist, introduced his model of the hydrogen atom. Introduction to Bohr's model of the hydrogen atom. In this lesson, you will learn Bohr's postulates of the hydrogen atom, to derive the expression for the radii of the orbits of the electron in the hydrogen atom, to derive the expression for the energy of the electron in the various orbits. In 1911, Ernest Rutherford and his colleagues used a stream of alpha particles to bombard a piece of gold foil. Click the Rutherford's alpha scattering experiment button. Notice that most of the alpha particles were scattered or passed through the foil as if the foil were mostly empty space. Few were deflected at very large angles. This observation cannot be explained using J. Thomson's model. To explain this observation, Rutherford theorized that the atom consists of a massive positive charge concentrated in a very small region called the nucleus of the atom. The electrons orbit around the nucleus just as planets around the Sun. Click the Zoom button. Rutherford's model contradicts Maxwell's electromagnetic theory. According to this theory, an accelerating charge emits electromagnetic radiation. An electron orbiting the nucleus has a centripetal acceleration, so it ought to be continuously emitting electromagnetic radiation. Hence, it loses energy and should spiral into the nucleus. This means that this model of atom would not exist. Observation also shows that atoms do not emit continuous spectrum of electromagnetic radiation but line spectra. Summary. In Rutherford's model of the atom, an atom consists of a positively charged nucleus where most of the mass of the atom is concentrated and electrons orbit around the nucleus. Rutherford's model could not explain A. Why an electron should not spiral into the nucleus, B. Why atoms emit line spectra instead of continuous spectrum. Bohr's model of the hydrogen atom consists of two postulates. Click the Bohr's postulates button. The lowest stationary state is when n equals 1 and is known as the ground state. When n equals 2, the stationary state is known as the first excited state. Click n equals 2. The first excited state. Observe the motion of the electron and note its angular momentum in the table. Click n equals 3, then n equals 4. Suppose the electron in the hydrogen atom is in the third excited state, n equals 4. Click the n equals 3 button to observe what happens when the electron drops from the third excited state to the second excited state. Click the n equals 2 button to observe the transition of the electron from the stationary state n equals 3 to n equals 2. The electron is also able to drop from the stationary state n equals 4 direct to n equals 2 or n equals 1. Click the 4 to 2 button. Click the 4 to 1 button. Summary. Postulate 1. The electron in a hydrogen atom can only move in allowed circular orbits. In the allowed orbits, the angular momentum, Ln, of the electron is given by Ln equals nh over 2 pi. N equals 1, 2, 3, 4, 5, where h is Planck's constant. Postulate 2. The electron in an allowed orbit or stationary state does not emit electromagnetic radiation. The electron can make a transition between stationary states through the emission or absorption of a single photon of frequency f. Energy of the photon hf equals delta E, where delta E equals difference in the energy of the two stationary states. When an electron moves round the nucleus, the centripetal force is provided by the electrostatic force. Click the derivation button to deduce the expression for the radius Rn of the orbit of the electron. For the hydrogen atom, there is only one proton in the nucleus. For the ground state n equals 1, click the calculation button to determine the radius R1. Click the n equals 2 button and then the n equals 3 button. What is the relationship between the radius of the nth orbit Rn and R1? Answer: Rn equals n squared R1. Summary. The centripetal force required for an n electron to orbit around the nucleus is provided by the electrostatic force. If R1 is the radius of the first orbit, the radius of the nth orbit Rn equals n squared R1. The total energy of an electron in a Bohr's orbit is the sum of its kinetic energy K and potential energy U. Click the derivation button. In the hydrogen atom, Z equals 1. For the ground state, N equals 1. Click the calculation button to determine the energy E1. What is the relationship between En and E1? Answer: En equals E1 over n squared equals minus 13.6 over n squared electron volt. The energy of the electron in the various stationary states can be represented in an energy level diagram. Click the energy level diagram button. Summary. The energy of the electron in an atom is the sum of its kinetic energy and electric potential energy. The energy of hydrogen atom in the ground state is minus 13.6 electron volt. For hydrogen atom, the energy of the electron in the nth stationary state is given by En.